Yeah, like as usual, my usual question, other questions from last time. And as usual, there is no answer. So maybe we can start. So last time we were talking about this quantum synchronization. And we said that, okay, one way to do it is to say that I have a quantum harmonic oscillator which is interacting with a bath. And we wrote down the equation for the time evolution of the density operator of the system. It had this particular form. Okay, maybe I'm confused. Where generically these jump operators are defined like this. Okay, and this Hamiltonian is the Hamiltonian of a quantum harmonic oscillator. Okay, and then we said that, okay, one way to understand that this is really the one photon gain, and this is really the two photon loss term. One way to see it is to take the matrix element, sorry. So this is by definition the probability that the system is in the nth energy eigenstate, or that the system has got n photons or phonons, whatever, the quanta that you are dealing with. So then this equation will give you this is small. Okay, so this is where we stopped last time. So I guess there's no issue with this equation, right? And now you know how to play the game. Suppose I want to have, sorry, suppose I want to have some other jump operator here. For example, sometimes they look at this case, perhaps I have it later. Okay, suppose you want to have some combination, I don't know, like let's say A dagger M A N. Okay, suppose I want to have a process of that sort, whatever that means. Okay, this is my choice. So then what I have to do is I have to just apply this formula here. So what you do is that you take this formula and replace O by A dagger M A N. Okay. In fact, later we will see, or at least even if we don't get there, you will see in the notes that there is a setup in which the quantum harmonic oscillator is subject to an external drive, and there the form of this operator is different. Whatever is the form, you can always write that down in terms of this A dagger A, and then you plug it in here. And the best way to understand the physical meaning of a term is to look at the matrix element, because then it takes up the form of a master equation, and this is a classical object. There is no quantum about it. These are real numbers, okay, and of course they satisfy, since trace of rho is equal to 1, it just means that okay, so this is a bona fide probability, and so it is normalized to 1 and everything is well defined. Okay. Yeah. Okay. So now what is the thing? That you want to see something out of it, something coming out of it. Let's say you want to know about the stationary state of the system and so on. So what you do is that in the stationary state you set the left hand side to 0 and try to solve these equations. But these equations, okay, there are going, for the quantum harmonic oscillator, n runs all the way from 0 to infinity. So you are going to get an infinite number of coupled differential equations. Thankfully, these are linear. You see, P appears always as a linear term in this equation. But anyways, you have to, you have an infinite number of coupled linear differential equations, and that you have to solve. So the only recourse is numerically. It turns out that there is a package which is very popular, okay, which is this Q-tip. Some of you, did anybody have an experience of using this package, Q-tip? Even I don't have, so no problem. So, but my students tell me that this is very, apparently it's like a black box. You give this thing and then something comes out of it. Something meaning something trustworthy, not trash. Okay. But then what do I do with it? So you cannot do much. So you have to, do something else. Okay, and what is that something else? That is what I am going to talk about today, what is known as the Wigner function approach. Achha, before that I need a little bit of background on coherent states. What is it that we want to do? We want to see some signatures of some oscillation, some limit cycle, something of that sort. So therefore, before we get to limit cycle, we, just as we did for the classical case, we dealt first with the closed system. That is, we first dealt with the harmonic oscillator, simple harmonic oscillator, in the absence of any damping, in which we saw that there is no limit cycle. There is just a closed orbit that you see. So the thing is that we want to first understand that particular setup, and then we will deal with these cases where there is there is dissipation in the system. So I need to tell you about some basic results of quantum harmonic oscillators. So let me first find them. Yeah. Okay. So so what are these coherent states? But before I get there, let me first. So I'm just reviewing some basic stuff from quantum harmonic oscillator, closed system. Okay. So as I've written down, I will keep forgetting to keep the put the hat, but that's fine. You can live with it. Okay. And you define these operators, these creation and annihilation operators. A acting on n is equal to square root of n times n minus 1. This is the annihilation operator, this is the creation operator. So we are going to interpret it this way, that if there are n photons or n quanta in the system, this is going to kill one. That is, you jump one step below, one state below, and this when you have n phonons or photons in the system, you jump one step up. So you create n plus one more photons, one photon, so therefore you go to this one. Okay, now you may ask the following question, that suppose I prepare the system. Okay, the general question that I would like to ask is the following, that in the classical case, let's say this is the quantum harmonic oscillator, where on the other end, when you have the classical harmonic oscillator, you know that this x, it oscillates as a function of time, with an equation which is of that sort. Okay. So the question is, what happens, what is the quantity that I should look at which would show an oscillation of the following sort: x is equal to x naught cos omega t plus phi, and similarly p is equal to the momentum sin omega t minus phi, and so we want to see what is the thing that I should compute here that would show a behavior similar to that. So on the face of it, you may say that, okay, first of all, these are classical, these are numbers, real numbers. So here, of course, I have to compute some quantum expectation. So a naive guess would be that I take the same quantity, I construct the corresponding operator, and I find its expectation. Now expectation, I have to decide as to where do I want to compute the expectation in which state do I want to compute the expectation. You see, there is a time dependence here. So I ought to have some time dependence there in order to have some mapping between this and that. But then suppose I compute it in an energy eigenstate, surely I won't have any time dependence, because if an energy eigenstate will not have any time evolution, okay, because the system is closed, it's coherent, so therefore the evolution is coherent, so the coherent and unitary, so therefore an energy eigenstate, if I prepare the system in this state at time t equal to 0, then it is going to remain there forever, okay, wherever t is equal to 50, it is going to remain the same. So this quantity surely will not gain a time dependence if I compute the expectation in an energy eigenstate, or I compute it in compute the expectation of p in an energy eigenstate n, I will not get such a thing. In fact, this one will turn out to be 0. You can just check it. The way to check it is to express x in terms of a and a dagger. Perhaps I should write down quickly the definition of a and a dagger in terms of x and p. So x is square root of h bar by 2m omega a plus a dagger, and p is I root of m omega h bar by 2 of a dagger minus a. So now, then the question is, what is the state in which I should compute the expectation in that would show these oscillations of the sort that is there. So these states are what are known as the coherent states. So instead of computing x in n, expectation of x in n, suppose I compute x in some state alpha, which I will come to in a minute, and p in some state p, then I will see that this is not equal to 0. In fact, they will have identical expression as the classical one. So what is this state? I guess some of you know about it, but anyways. So what are these alpha states? So surely if I prepare the system in an energy eigenstate, it will remain there. But what if I start with an initial condition in which I take a superposition of energy eigenstates? Then of course there will be some time evolution. One state, of course, there will not be any time evolution, but some superposition will have some time evolution. So this alpha, it is a particular superposition of these energy eigenstates, which has this particular form. It's a very particular linear superposition. So linear superposition means I have to superpose the energy eigenstates, but then the coefficients here have particular forms. Okay. Of course, I mean this coefficient, it has to be all the square n factorial and blah blah blah. You need just to have it normalized, like ortho, this has to be normalized to 1, so that's why you need this factor. I guess some of you may see if I do, if I act on it, if I put a bra here, then I'll get nm, and these are orthonormal. Maybe I should write somewhere nm is delta nm. So orthonormal means you will get some alpha mod squared to the power 2n by n factorial. Want to cancel this with that so that you get 1. So that's why these factors, they come in a particular combination. But what is this state? This turns out to be the eigenstate of the annihilation operator. Sorry. Okay, so these coherent states, these are eigenstates of the annihilation operator that have the property that, first of all, it's a state that is a linear superposition of the energy eigenstates. Secondly, okay, they have a bunch of properties. I have mentioned them and have them as part of the exercises. They have a bunch of properties. So one property is that it is the eigenstate. Second property is that if you compute the expectation of x in a coherent state alpha, then you get an expression which is exactly identical to the classical expression. What you get is, of course, there is a constant factor here, which is 2h bar by m omega alpha mod. Okay, this is some constant factor, but the time dependence is exactly like what you have in the classical case, cos omega t minus phi, and so is the case with the momentum operator. If you compute the quantum expectation there, you pick up a time dependence because you are starting with an energy, a linear superposition of energy eigenstates. Again, there is some constant factor here, 2m h bar omega alpha. This is inconsequential, but then the time dependence is exactly like the classical case. There is one more property, that if you prepare the system in a coherent state, it remains always in a coherent state. It just picks up a phase. So that is to say that suppose I prepare the system in a coherent state alpha. Let's say I prepare the system psi t equal to 0. If this is equal to alpha, then the system always remains in a coherent state, excepting to pick up a phase. So let me see, how does the phase look like? Yes, it is e to the minus I omega t by 2 of alpha e to the power minus I omega t. So I guess you understand the physical notion of a coherent state. It's a linear superposition of energy eigenstates. It's a very particular superposition of energy eigenstates, namely of this sort. It is an eigenstate of the annihilation operator. Moreover, if you prepare the system in a coherent state, you remain always in a coherent state, excepting for some phase factors. Okay, it is still a coherent state, because if you act on this state by A, you will get this phase factors, nothing else. Huh? Yeah, just 1 minute. No, complex number. Complex number, yes. That's why I have put alpha mod square, yes. Because you see, A is not a Hermitian operator. If you look at it somewhere, okay, A is, A dagger is, A and A dagger, they are different. Okay? So A is not a Hermitian operator, so this is not an observable, and therefore the eigenstate, eigenvalue doesn't have to be real. Okay? So that's why you get an alpha mod square here. What is this phi factor that I'm writing here? The phi factor, it just comes from writing alpha as, alpha is a complex number, so you write it as alpha mod e to the power minus I phi or plus I phi. It's just a convention. Plus I phi. Okay, it's just a convention, doesn't matter. There are other properties that one can talk about. For example, this one very nice.
This is not obvious for me how you computed the expectation value of X.
Yes, it requires some doing. Okay, so what you have to do is that you express X in terms of A and A dagger. Okay, so then what you do is that, how do you define this guy? So how do you compute this guy? So what you have to do is alpha. So what you have to do is, this is the expectation in state alpha, so you have to do this. Right? And X, I know how to write it down in terms of A and A dagger. This is square root of h bar by 2 m omega of A plus A dagger. So I do alpha A plus A dagger alpha. Now I know what A alpha is. A alpha is alpha alpha, and so on. Okay, so you combine these two, you at once see you will get a cosine because it's a sum. That's why you get cosine. Okay, because alpha I write it as alpha mod e to the power I phi.
And from there, omega t appears.
Oh, okay, good. So like omega t appears because what I am doing is that I am computing it at time t. Sorry. Okay. Okay, I'm computing it at time t. At time 0, of course, no omega. Okay, I'm computing it at time t. Sorry, I should put a t here. I thought it is obvious. Okay. So at time t, I want to compute the expectation, but at time t, how does the alpha states evolve? Alpha t. So what I need to do, I need to know alpha t, right? But alpha t is nothing but alpha, whatever was the value at time 0 e to the minus I omega t. This is what I have written here. And alpha is alpha mod e to the power I phi.
So there is not that exponential that you put before the alpha t for psi t.
No. This is for psi t, but for alpha becomes like that. See, this exponential comes because when you act on it, yeah, I mean, this you have to just do it, I guess, okay. Because this will satisfy the Schrodinger equation, so that's why you get that factor. Okay, I've given some exercises, so let me just see if I can get there, which are let me see. This one. Okay, so this, this displacement operator and this and that I skip because I don't need it. Okay, one last thing that maybe I can point out, which is kind of remarkable, is this one. Okay, so alpha I know. Okay, so this is an eigenstate of the annihilation operator. But what do I need to know? What do I need to do to find the corresponding wave function? This is a vector. This is a wave vector. This is a state. What do I need to know to for alpha? What do I need to do to get the corresponding wave function? What do I need to do? Huh? Sorry? Get from this side? No. This side could be this, right? X, no? Bra. Huh? It's you know why is it called bra and ket, right? Why is it called bra and ket? It's bracket, no? It's a bracket is like this. This is bra, no? This is like this, no? This is bra and this is ket. So this way it cannot be bra, okay? It cannot be ket. Then bracket would have been called ket bra. The easy way to know. Okay, so suppose you compute this guy. Again, it's a very straightforward thing, but still, I mean, it is given as part of the exercise. So this has a form that looks very nice. That reminds one of some quantity that I will define in a minute. Where this what is this delta x alpha? This is by definition square root of x square alpha minus x alpha squared. And if you do this, then you get h bar by 2. Okay? So let's see, what am I trying to do here? I want to know, given a coherent state, what is the corresponding wave function, okay? So what I see is that this wave function has this Gaussian form. It is centered at x alpha, and what is x alpha? This is this alpha cos omega t minus pi, okay? So what it tells you is that in the classical case, you have a particle, your classical harmonic particle, which is just doing this oscillation. In the quantum case, instead of being just a point doing the oscillation, you have a Gaussian. The Gaussian is oscillating. The center of the Gaussian is what is the motion of the center of the Gaussian is the same as the motion of the corresponding classical like particle. Yeah. What is the center of the Gaussian? It is x alpha. X alpha, it has the same expression, same time dependence as the classical one. So what you understand is that what quantum mechanics is doing is it is just adding some quantum fluctuations to the system. In the classical case, you have just one point which is doing like this. In the quantum case, you have a wave function, okay? The Gaussian is doing like this. The width is time independent. The width is not changing. So it is not that I have a Gaussian that is spreading and doing like this. No, the width remains the same, but it just does like that. Okay. On YouTube and all, you can find a lot of videos, or you can run your own code to see. But I need this coherent state in order to discuss limit cycle, because now that I see that something is oscillating, it rings a bell. It rings a bell in the following sense, that perhaps I can do something with these coherent states in order to get limit cycle, some oscillatory behavior. Because if I start with an energy eigenstate, it doesn't work, because nothing oscillates there, you just remain there. But if I start with a coherent state, I remain in a coherent state, and in a coherent state, when I compute the quantum expectation of the position and the momentum, I get the same expression as I have for the classical case. So therefore, that kind of tells me that perhaps I have to do something with these coherent states, not with energy eigenstates, which are boring objects. Okay? Are there questions from this part? Do you see what it is? What is going on? How do you define? Now these algebra you have to do, and they should not take more than 10 minutes to do. Okay, so you can spend 10 minutes of your life in getting this done. You have to just play with the orthonormality condition. The states are orthogonal to one another and they are normalized, and act on states by these creation and annihilation operators, and you will get these answers. Okay, nothing big, no big deal. Okay, are there questions on this part? Do you see? Huh? Yeah, this alpha, it already contains a linear combination of all these states. Okay, you can ask for the in a coherent state, what is the distribution of photons and so on. Okay, because it will not be just one number, it will be some, and that is given by a Poisson distribution. Let me just write that down. Yeah, so you ask, suppose you are in a coherent state alpha, and I act on it by the number operator. See, the way I can extract the number of photons in the system is by acting on it by the number operator, which is A dagger A. Okay, so I act on it and I get something. Okay, so what will happen is that you will get this thing. Let me see. So you ask, you see, when you act on a state by a number operator, okay, then what you will get is, if you had acted on n by this number operator, you would have gotten just n, okay, because you just get n times n by definition. But now what will happen is that since alpha is not an eigenstate of A dagger A, then each time you act on it, you will get a different number. Okay, so then there's going to be an expectation value, and so you may ask, what is the probability that I act on a coherent state by the number operator and I get the energy value En, or so to say, I get the number of photons to be equal to n. Okay, so this becomes this is a Poissonian distribution. This is why does this one, why is n an eigenstate of n? This small n, why is small n an eigenstate of capital N? What is the property that, of course I can check it, but even without checking, I can at once say that small n is an eigenstate of, see, small n is already an eigenstate of the Hamiltonian, and I claim that small n is also an eigenstate of the number operator. How can I say that without doing all this calculation? So? No, I am asking the following question. This n, this is an eigenstate of the Hamiltonian. But this is also an eigenstate of the number operator, where the number operator by definition is equal to A dagger A. Okay? I am asking what property do I need to conclude that n is also an eigenstate of the number operator? Yes, exactly. You see, h and n, they commute. Because, if I take h and n, they commute. Why they commute? Because h is what? H is A dagger A. H, I can write it as, okay, this is not the, this is the energy. H, I should have written it as A dagger A. Sorry. The energy. See, h and n, they commute because it's the same thing. So therefore, when you have two commuting operators, they will have simultaneous eigenstates. And so therefore, no wonder that it is also an eigenstate of this. But then alpha is not an eigenstate of the n operator because it's some complicated combination of these energy eigenstates. So it is not a, but then what will happen is if you act on alpha by n, you will get different values of the number of photons, and this is the distribution that you get. You can compute the expectation also and so on. Yeah, so that answers, I hope that answers your question. Okay. So if there are no other things, then let me just move on to Wigner function, because this is a very convenient way to, this has, Wigner has nothing to do with harmonic oscillator per se, but it is, helpful to introduce it. And then we can come back to our model. No questions, right? So let me just move on. Sorry? Oh, PEN, okay? It is the following. See, if you are in an energy eigenstate n and you act on it by the number operator, you get one and only one number, n. Okay? But suppose I do this following thing. What do I get? This is not an eigenstate of n. So what I will get is, according to the measurement postulate of quantum mechanics, if you act on a state by an observable, this is an observable by the way, okay? A dagger A is a Hermitian operator. So therefore I should get some real number, okay? Because when I act on this state by a Hermitian operator, I should get a real number. Now what quantum mechanics tells me is that I have a state, I have an operator, I act on the state by the operator. What I should be getting is, I should be getting the eigenvalues of the operator, okay? So sometimes I may get the eigenvalue lambda 1, sometimes I may get the eigenvalue lambda 2, lambda 3, lambda 4, lambda 5. In the same way, I may get n equal to 5, n equal to 7, n equal to 76, n equal to 554, whatever. So then I can draw the histogram. And I ask, what is the form of that histogram? The form of that histogram is like this. So what is the most likely value that I will get? 0, right? Because it's a Poisson distribution. No? Okay, so now I go to the Wigner. So Wigner, again, I mean, this is a subject in its own right, so I will of course not be able to do justice to it, but you may do justice to it by working out the exercises, because I have framed the questions in a way that you can start from ground level and take off, if not to the sky, at least somewhere higher than the ground level. Okay, so what is this coherent state? Let me see. Sorry, what is this Wigner function? Let me see if I can get there. How do I have it? Okay, should have it here. Okay, so Wigner asked the following question, that in classical mechanics, whenever I have a random variable and I want to compute its average, this is not a quantum average, this is a classical average of a random variable, and this corresponding to this random variable there is a probability distribution associated with it. I hope you know this convention, right, that x is the random, maybe I should write x here. X is the random variable and x is the particular, small x is a particular value that x takes up. So how do I do it? What I should do is I should do this. By definition, I find out the probability distribution and I multiply by x and that's it, okay? And in that sense, I can compute the expectation value or the average of any power of n, of x, okay? I need to do this. So he asked the following question, but in the quantum mechanics case, when I want to know the quantum expectation of an operator, I need to do something different. What I need to do is I need to multiply rho, O, the operator I am interested in, with the density operator of the system and then do the trace operation. Okay. So he was asking, is there a way that I can, instead of doing this trace operation, do it as some O of some O, P, O, D, O, something like that. Can I do like this? Of course, I have to be clever enough in coming up with the definition of P, O. O is particularly, like easy to define because, O is an operator, so maybe what I should do is I should look at the eigenvalues of O and those are real numbers because it's an observable. But P of O, what is this guy? Okay, so that was the motivation behind introducing the Wigner function. By the way, before I move on, do you know why, what is the advantage in having a trace operation here? What do I get if I get a trace? I mean, I should be overjoyed that I get a trace because some part of the calculation becomes particularly easy if it's a trace. No, not necessarily, but it is independent of the basis in which you compute. Okay, rotation is something different. Okay, that depends on the form of your dynamics operator, etc. So the trace is that you can compute it in any basis, any complete set of orthonormal basis, and then the trace will remains invariant. Okay. So now the question is, what is this guy? How do I define this guy? So the definition of course, it has to be somehow related to rho, because on this side I have rho, so this P of O has to be related to rho in some way. So what he said is that given a density operator rho, this is very general, and I'm at the moment doing it for a single particle case. Okay, so you define a quantity WXP, which is the following. So you take the density operator of the system, you sandwich it between x plus y, x minus y. Okay, these are the eigenstates of the position operator. And then you do e to the power I twice Py by h bar, and then you integrate over y. Or this is one way to define it, or an equivalent way is you define it in terms of the, there is a 1 by pi h bar. Or there is a 1 by pi h bar. And an equivalent way is you define it in terms of the eigenstates of the momentum operator. So you get P minus Q rho P plus Q e to the minus I twice Qx by h bar. Okay, this is just a definition. So what? How does it simplify my life? Doesn't seem to be simplifying my life. But you see, if I do the following thing, dx of wxp, okay? Let's do it. It's very easy. Dx of wxp, so I take this one. I want to integrate with respect to x. So which formula should I use? This one or that one? Which one will make my life simple? If I want to integrate with respect to x, second one, right? And if I integrate with respect to x, I'll get a delta function in q, q0. So therefore, what I will get if I do the integration over q, I get basically p rho p. And similarly, dp of wxp is nothing but x rho x. But now comes the best part of it, that is, that suppose, as I was saying, is there a way to do quantum expectation if can I do like this? Suppose I am given an operator O, okay? So can I do this thing? So what I do is that first I take that operator O and then construct this quantity. It is constructed in exactly the same way as you constructed there, excepting for this 1 by pi h per factor. Okay. Then of course the quantum expectation I know from my course on quantum mechanics is given by trace of rho times O, but using this definition what I can do is I can show that this is nothing but okay, let me make some space here. So I take my operator O and then I construct this function which is a function of, can you tell me what is this a function of? X and P, right? I got exactly what I wanted. What I wanted was, I wanted the quantum expectation to be computed as averaging with respect to a classical number, some probability distribution. So it seems, if I look at this formula, it seems as if W is the probability. W is the probability to get X and P. I multiply it by the quantity that I am interested in. Of course, I have to construct the corresponding. So I cannot deal with I cannot put an operator here. So because this is this thing is a number, so it's not an operator. It's a C number, a classical number. So what I need to do is that I take this operator and I construct a new function which is taking the operator and sandwiching it between the position eigenstates and multiplying it with a factor. Once I have done that, then the computation of the expectation value boils down to doing some classical integration, averaging with respect to some probability distribution. I don't have to worry about trace and operators and this and that. Okay? So it's a huge simplification. The bad news is that this W guy, it is discussed in the text. I mean, it seems as though this is like a probability distribution. Not seems, I mean, if you look at it, you will at once say that, look, this looks like a probability distribution. But it turns out that it is only a quasi-probability distribution in the sense that W itself can sometimes be negative. Although a W can be negative, yet all these integrals are perfectly well defined. So therefore, if you have to compute the quantum expectation of an operator, so either you go via this traditional route, which is trace of this, or you construct the corresponding This is what is known as the Wigner transform of this operator. Take this operator, you do this, I think it's also called Well transform probably. Okay, and this is that. Okay. There is one more remarkable fact about this W, which I will just state, and again it is stated as an exercise, so you can do it. You see, how does rho evolve as a, what is the definition of W? Okay. Can you tell me if W is a time dependent function or a time independent function? In the sense that does it have an explicit time dependence? Should it have an explicit time dependence? Yes, right? Because rho itself is changing as a function of time. Rho is changing according to the von Neumann equation. So therefore, if rho changes, so should W. So therefore, one may wonder what is the time evolution of W like. Okay? See, once I have found out the time evolution of W and then doing this quantum expectation in terms of classical averages, then I can reduce the quantum problem. I mean, not reduce. I can look at the quantum problem as though I am doing a classical problem. Okay, that I have some classical numbers and I have to do just some integration. No more tracing, wasting, etc. Okay, those things go for a ride. So what is the time evolution of W? This is again, given as an exercise, so therefore I will not do it. Just write this down. So this is for a single particle. Single particle means the Hamiltonian is of this sort, p square by twice m plus v of x. Very general. V could be anything, not necessarily quantum harmonic oscillator. This n has nothing to do with the quantum harmonic oscillator's number of photons. Okay, I have to make some space because it's a long formula, but still I want to write it. Yeah, okay. So what I have done is that I take the definition of W. I know how rho changes as a function of time according to the von Neumann equation. I just plug this in here, and then you have to do some algebra, which are all the details are all spelled out in the notes, so you can just do them. And if you do that, then you find that W changes as a function of time according to this equation. Okay, the first term is quite simple, but in the second term you see that you get terms which are of order h bar square, h bar, so the leading term is of course 1, I mean there is no dependence on h bar square, because when you put n equal to 0, then you put n equal to 1, you get h bar square, h bar 4, h bar 6, h bar 8, etc. etc. But let's look at this equation to lowest order in h bar, which is h bar to the power 0, and you will at once see what equation you get. Suppose I take, just for fun, take only n equal to 0 term in this expression. There is a v here, I think. Sorry, there is a v here. This is what you get if you just take the n equal to 0 term there. Okay. can you tell me whether you have seen such an equation before? Del t of some probability is equal to minus p by m this, and you know I can write del v del x as something and p by m as something. Okay, let me put it slightly, since it's suppose I take this equation and I use the Hamilton equations. Q dot is equal to p by m and p dot is equal to minus, sorry, x dot. Okay. X dot is equal to p by m, and this is this. Where have you seen such an equation? Yes, so this is nothing but the Liouville equation, classical Liouville equation. If you interpret, you know, it has the, let me put it this way, it has the same structure as the classical Liouville equation. This doesn't mean that I have reduced a quantum problem to a classical problem. No, it has the same structure as the classical Liouville equation. Classical Liouville equation exactly has that form, that del rho del t plus rho h equal to 0, and if you just expand it out, what you get is exactly what you have here. Okay, del rho del, you know, this is exactly what you have in the. So therefore, what Wigner has been able to do is to have an equation. First of all, the first achievement is to come up with a notion of a probability that has resemblance with classical probability. In the classical case, whenever you have some randomness, you have a probability distribution and you average over that randomness by, you know, multiplying with that probability distribution your quantity of interest and then integrating over all possible values of that random variable. In the quantum case, what is the source of randomness? The randomness is because of the quantum nature of the system, that when you have an observable, when you act on a state by that observable, instead of getting one value, you have 10,000 possibilities. You are going to get one of the different eigenvalues associated with the observable. So there is quantum randomness just because of the quantum nature of the system. So Wigner is asking, can I treat this randomness, quantum randomness, in terms of a probability distribution or a histogram? And the answer is yes, you can do that, provided you define a quantity of this sort, WXP. You need this H bar. Can somebody tell me why do I need all this H bar, etc.? By the way, I forgot to, perhaps intentionally, forgot to write down one integral concerning WXP that I ought to have written down in order to make it qualify as a bona fide probability distribution. What is that integral? Huh? You have to speak up. Normalization, exactly. You can check that you take this function WXP and then you multiply by x and you multiply by p, you get exactly equal to 1. This is exactly what you need for it to have the interpretation of a probability distribution. And now you know why you need this pi h bar. Why do you need this pi h bar? What is the dimension of W? 1 over h bar. Okay, so therefore W has exactly 1 over h bar. Why 1 over h bar? Because this is a number. So W has to have the dimension of 1 over xp. So this has to have the dimension of 1 over xp, and xp has the dimension of h bar. So that's why you need an h bar. Pi is because when you do this delta function, you get a 2 pi there, you want to cancel off and so on and so forth. So that is not so. Okay, so the first thing is that I can forget about dealing with operators. I can just define a quasi-probability distribution just as in the classical case, and then whenever I have to compute some expectation and all, so then what I do is that I just integrate my observable. I first take the Wigner transform of that observable. I get a C number, I multiply it by the probability distribution just as it is done here. So what I do is that this is the traditional route. But with Wigner's set is that no, you don't have to deal with matrices and multiplying and blah, blah, blah. What you do is that you take the probability distribution, you express your operator in terms of x and p, and then you do dx dp. More than that, if I want to write down the time evolution equation of W, it has striking resemblance with the equation that one writes down for the probability distribution of the phase space density in the classical case, namely that it has the leading term is of that order, of that form, classical Liouville equation. But you see there are quantum corrections which are put in, not put in, I mean they just come out of the calculation, and you see there is a systematic way in which the quantum corrections appear in this equation. So therefore you may say that okay, I don't want to study this in full generality, but then I want to see quantum corrections up to order h part to the power 56, okay, only like even order terms appear. What you do is that you take this infinite series, you truncate at 56, you get an answer. You say, is 56 good enough? No, let me be a bit more brave and go to 57. That is also quite easy to do because you just take one more term. Okay? I hope this introduction to Wigner, so I urge you to read the original paper of Wigner. It dates from 1932 and 1931. But it's a beautiful paper. I mean, those were the days when people would not be hesitant to say that they don't know something. Okay, just as now is the time when we all know everything. Okay, but those were the days when people would say, no, I don't know something. Let me just give it a try. And Wigner's paper was written exactly from that perspective. That he says that look, I'm groping in the dark and I don't know how to deal with things. Let me give it a try. And so the paper is written as though he is striking a conversation with the readers. Okay, he's just inviting the readers to go along with him. Okay. So other questions on W, because now what I'll do is that I will apply this formalism to the quantum harmonic oscillator, first closed and then open. And why do I do that? Because it allows to see the oscillation and the limit cycle in a very nice manner. Okay. First let us see, before I go to that part, are there questions on this Wigner function? Of course, I mean there are questions, but are there urgent questions? Some questions can, you have to look up. This is a standard textbook material, but still I urge you to read from Wigner's paper. It's okay, the motivation is clear, what you want to do. And why is it a good thing to do? Because then you don't have to, the problem in dealing with operators is that you have to worry about whether the operators are commuting or non-commuting and this and that. But if you have some integrals to do, some classical integration, then you don't have to worry about whether something is commuting. Everything is commuting with everything else. So then you don't have to worry about this, that, etc. So that's a good thing about it. Okay. And again, the the von Neumann equation, again this is an operator equation. You can write down a formal solution, but then again it's an operator equation. Instead, this is just a normal differential equation. There is no operator here. Everything is a C number. Okay, so therefore it's much easier to deal with in this picture than in that picture. Okay, now we come to quantum harmonic oscillator and see what we can do with the help of that with the Wigner. First, let us look at what is the picture that we had talked about in the classical simple harmonic oscillator. What we had said is that there is a periodic motion. This is a closed system. There is a periodic motion of x and p. X changes periodically as a function of time and p changes periodically as a function of time. So we had this picture, the very first picture that I had drawn or that the computer had drawn for me, which is that if I fix my value of energy, then what I get is I get a closed orbit in this phase space. The interpretation is the following, that if I start from this initial condition, then I have a point here. This point in course of time evolution is going round and round. Okay. So the point to note is that at any given instant you have just a point. You don't have the whole like ellipse. You have a point which is doing like this. Okay. You would think, well, in the classical simple harmonic oscillator, it's a closed system, there is no element of randomness. Okay? The only element of randomness that you may think about is the initial condition, but let's say I start with one precise initial condition, so therefore I start with one precise point and this point is just going round and round. There's no randomness here. Suppose I play the same game in the case of quantum harmonic oscillator, a closed quantum harmonic oscillator. Okay? What we saw from the discussion of the coherent state and this and that is that what I should expect is, in the classical case I have a point, perhaps in the quantum case I have a blob, okay, kind of a blob, in the class, we saw in the case of simple harmonic oscillator, classical and quantum. In the classical case, you had a point which was doing like this. In the quantum case, you have a Gaussian distribution which was doing like this. So perhaps I have a blob here. Okay, instead of being a point, I have a blob, and the width of the blob has something to do with h bar. Okay, because the system is quantum, so there is quantum randomness in the system, and so therefore I have a blob here, and that blob should be going round and round. Okay? But then the question is, what is the space in which I should plot the blob? Surely I cannot talk about x and p phase space for a quantum system. Why I cannot do that? I cannot, x and p, they don't commute. xp is equal to I h bar. So therefore, if I know x very well, I don't know, I have no idea about p, and p will have a lot of uncertainties and vice versa. So the phase space that I need to draw for a quantum system cannot be this xp phase space. In fact, there is no notion of phase space. What I should do is something that I am going to tell you, but certainly it cannot be this xp space. So I have to construct a particular space in which I can do this thing. But Wigner function now tells me what I have to do. What I do is that I take the quantum harmonic oscillator. It's a quantum system. Whenever I have to do, whenever I have to compute quantum expectation, I have to do trace and this and that. But what I do is that I take the quantum harmonic oscillator, I study it in terms of WXP. That is, I reduce the whole problem to a problem couched in the language of a Wigner function. And these are classical objects. So what I can do is, once I have reduced this to WXP, and then if I look at the motion of WXP in the XP plane, then I should get a blob which is going round and round. In the quantum case, I cannot do it, because I don't have the luxury of treating the phase space as constituted by x and p. They don't commute. But once I have reduced this problem to an apparent classical problem, it is not truly a classical problem, because as I mentioned, WXP, it may have some negative, negative entities. I mean, it is not real, although all the averages are well defined, but the quantity itself may become negative. Okay? So what I should do is I should look at the corresponding problem framed in set up in terms of the Wigner function, and look at the motion of the Wigner function as a function of time in the XP space. Okay? Of course, like traditionally what you do is, you see, in the quantum case what I had was, I had the quantum expectation of x and p computed in an coherent state oscillating. So therefore I better express this in terms of the coherent states. Okay, and then I compute x of alpha by doing this sort of an integral. I express it as a function of alpha. I do this. Is this expression clear? What am I trying to do here? While you wonder whether it is clear or not, I look up my notes to see if I am using the right notation.
Excuse me.
Huh.
I didn't understand why you can't use us in XP.
Because xp are non-commuting. How do you extract x and p? They are non-commuting
For
operators.
example, instead of having an exact point, you can have an area that it's.
Yeah, but then the space itself is not defined. See, how do you construct the phase space? What you do is that you look at the state of the system. The state of the system is given by the value of the position and the value of the momentum. The state of the system is like a dot in the phase space. In the quantum system, you cannot measure simultaneously x and p with equal precision. You do not even know the state because they are non-commuting.
So I think instead of having an exact point, we can instead of it have area that its area is proportional to h bar, and we can still.
Yes, that is exactly what I am doing here. But then you have to look at the function w. See, what w is doing is w is indeed it is characterizing the randomness which is there. When you have a blob, you don't have one point, right? You have many possibilities. And w is characterizing that many possibility option. W is a probability distribution. So it tells you what is the probability that you get x and p at time t. It's a quasi probability, but okay. Okay. So this expression is correct. So what I do is that I take my definition of x and p, and then I know x and p, they both can be, the corresponding operators x and p, they both can be expressed in terms of a and a dagger. Okay. Then what I do is that I consider instead of w as a function of x and p, I consider w in terms of the eigenvalues of these eigenvalue of this operator, which is alpha, alpha star and t. So there are explicit formula for it, which like again I have indicated in the text how do you get it, but this one is a bit non-trivial, but let me again just write that down. Okay. So W is defined this way in terms of alpha, alpha star. See, I had given a definition of W in terms of rho, but now what I want to do is I don't want to do a variable transformation. In terms of talking about x, instead of talking about x and p, I want to talk about a and a dagger and the corresponding eigenvalues, alpha and alpha star. So now this definition becomes a bit complicated, but not too much. Alpha, where what is this chi of z, chi s of z? This is what is known as the characteristic function. Of rho. One can show that these two definitions are exactly equivalent, but like again you have to sit down and do it. So what I am doing is that instead of writing the W as a function of x and p, I want to write them in terms of the eigenvalues of the annihilation operator, alpha and alpha star, coherent state representation. Okay, so it turns out that this is the representation. You have to do a complex integration over this complex variable z in the complex z plane. So this is defined like this. And once I know this, then what I can do is that I can compute this function and plot it in the alpha star plane, or typically it is done in the real alpha imaginary alpha plane. You see all these things, there is a one-to-one mapping. Instead of talking about x and p, I talk about a and a dagger, and instead of talking about a and a dagger, I talk about alpha and alpha star. So, I mean, there is no point in the calculation in which there is any cheating involved. You are just doing transformation of variables. You are going to variables in which things are more clear and transparent. Why I want to do it in terms of alpha and alpha star? Because I know that in a coherent state you have this periodic motion. Okay? So let me now show you at least one plot for the quantum harmonic oscillator. Yeah, this is the one that sorry. I hope you can see. Okay, so what is it that I have done here? So what I have done is that my axes are now real alpha and imaginary alpha. Okay, as I have mentioned, I want to look at the motion of the Wigner function in the alpha star or real alpha imaginary alpha plane. Okay, these two are the same. So what I have here is, you see that initially I had started out with a blob there. Okay, so this is my initial condition. You see the initial condition, instead of being a point, is a blob. Why? Because of quantum randomness. So that is the first plot, and the second plot, you see where does the point go to after a time, I don't know, this is probably t/4 has passed. Okay, so it has it has moved, it basically moves on a circle because I have done it for such parameter values. So this is one time, and this is after a time period. Let me see, it is period by 4 probably. Okay, 0 t/3 to t/3. Okay, so you see that the blob is moving. At any given instant, of course, the blob is somewhere, but then it is moving. And the last one shows simultaneously the location of the blob at 4 time instances: 0 t/4, 2 t/4, 3 t/4. Okay, the last plot here. So what you see is, you start off from here, then t/4 you are here, then 3 t/4 you are here. Then you keep coming back. So it is this blob is kind of moving. Okay, so this is the exact quantum analog of the classical motion. In the classical case, you had a point which was moving on this like ellipse. Now what you have is, you have a blob which is moving. Okay. How do I get such a plot? Of course, one possibility is to, this QT package that I told you about. What you can do is that you can, use it as a black box. But more than that, what you can do is, now this calculation is really very, very non-trivial. And again, I have it, at least in one of the cases, I have worked it out in the notes. So what you have is, you can write down the time evolution equation for W. Of course, you have to get rid of p's and x and write everything in terms of alpha and alpha star. So the best thing is to start from this equation. So you do a del t here. So the del t that you do here will be a del t here. Okay, because del t, there will be a del rho del t here. And del rho del t is minus I by h bar h rho. Okay. Then you have to deal with all these a daggers and a's. Okay. And you have to compute this trace and put them back. So it's a very long calculation, but it can be done exactly without any approximation. And if you do that, you get the function W alpha alpha star at different times. You plot them, you get exactly the plot that you have. So this is for a classical harmonic oscillator in which an initial condition just goes round and round, rotates. Closed quantum harmonic oscillator. So I have an exact equivalence between classical and quantum, and now you may ask, what is the situation that comes out of this of such an analysis if you now make the system open? That is to say, instead of del rho del t, before I get to that, do you understand how do you get a time dependency? How do I compute it? I do del del t. So these are not time dependent. This is time dependent. So I do a del del t here. Del del t here. So del rho del t here. And I know what is del rho del t. Del rho del t is equal to minus I by h bar of h rho. But h is nothing but a dagger a plus half h bar omega. So I have to plug this in here and do all these, you have to deal extensively with what is known as the Baker-Campbell-Hausdorff formula. How many of you know about it? Then I know that you can do the calculation. Baker-Campbell-Hausdorff formula that, let's say I am dealing with two quantum operators. Tell me this, if this is this true? So surely if these are classical numbers, this is true. But if these are operators, is this true?
Only if they commute.
So if they don't commute, then you get a long series here. So that is known as the Baker-Campbell-Hausdorff formula. What I need to do is, this is e to the a plus b. I write it in terms of e to the a, e to the b, and then a lot of other terms. And then I know the commutator of a dagger with a and a with a dagger and so on. So I need to do this thing. So it's a long calculation. And if I do it, I get that. But now you may ask, what happens if I play the same game, but for a closed, not closed, for a quantum harmonic oscillator which is open and exactly of the sort that we had talked about, which is gamma 1 of d of a dagger rho plus gamma 2 of d of a square rho. See, this was the open quantum harmonic oscillator that we had talked about. Again, the analysis is exactly the same. What I do is that this is the parent definition of W. I del t here, I get a del t here, and del rho del t. I plug this whole beast there, and I do the computation. Again, this is an even longer computation, and if I do it and if I plot it as a function of time, then what I see is what I see here. So let's see what I see there. See, this initial condition is the same. I started out with a point. In the case of the closed system, the point, instead of being point, of course, it was like a blob, and the blob was moving. But now, because the system is interacting with the heat bath, with the photon bath, the blob moves as well as spreads. So you see this blob, it has moved, the center has moved, but it has also spread out. And the longer I wait, this is t equal to 0, this is a little time later, it has spread out somewhat. The center has moved and also it has spread out. If I wait even longer, it has spread out even more. And I keep going, this has spread out quite a lot. And it has completely spread out over the entire cycle. See, in the classical case, I could not have had it, classical harmonic oscillator, closed. I would have had just a point which is either here or here or here. Here, you see that one point has spread out over a complete circle. And why I show this one and that? They seem to look exactly the same. Why do I do it? To show that the system has attained a stationary state. A state in which the initial point has spread out over a circle. In fact, to impress you, this is for one given initial condition, and the initial condition is set by the set by the like initial value of alpha. So I take one initial value of alpha, I do this game, I get to this stationary state, I change that initial condition, I go to another initial condition, and believe me, you get the same stationary state. So then I have been able to show what exactly I had seen for a simple harmonic oscillator that had some dissipation. That whatever be the initial condition, eventually you settle to a closed trajectory. That closed trajectory is independent of the initial condition. In the quantum case also, you have a closed trajectory that is independent of the initial condition, provided of course you let the quantum system have some interaction, because what does interaction do is to have some dissipation in the system in the same manner as the classical case had. And because I wanted some nonlinear term, you see in the van der Pol oscillator I had a nonlinear dissipation. The dissipation term was x dot of x square minus 1. It's a nonlinear dissipation. That is the reason why I have chosen here this term to be this is the 2 photon loss and this is the 1 photon gain. You can play with it. You can say, okay, I want to do 1 photon gain, 1 photon loss, 56 photon gain, 76 photon loss. Of course, you will get different limit cycles. But this is what is known in the quantum literature as a quantum limit cycle. This, of course, has got a particular frequency that you can extract. How do you extract the frequency of this quantum limit cycle? You have to do what? I mean, something that you do when you have some data to extract the underlying frequency, you do something. I mean, don't say Fourier, you look at a particular quantity, right? And it has a name. You look at the power spectrum, right? So you look at this quantity, S of omega, right? S of omega is, so it is the Fourier of the number operator. So let me just precisely write down the definition of it. Where is the definition? 1 minute. So, okay, this is the definition. Why this one is a good definition, that is also explained in the notes. And if you look at the power spectrum, okay, that's not coming. Oh, somehow the battery is over now. Okay, maybe the battery is over and the time is also over. So let me just quickly summarize. So what we started off, so my lectures have also come a full cycle. Okay, I started off with a simple harmonic oscillator, closed and some dissipation, van der Pol. The closed one did not have any limit cycle, it had just many closed orbits. They are all dependent on the initial condition. Then van der Pol is closed simple harmonic oscillator plus some open thing, which is the dissipation. And then you have a closed orbit which is independent of the initial condition. That was the starting point. And then we said there are many such limit cycle oscillators, and I want to know whether there is synchronization among them. Quantum case, you have a closed quantum harmonic oscillator, you have a blob which is going round and round. Everything is dependent on the initial condition. You let the closed quantum harmonic oscillator interact with a bath. Now instead of being a point, you have a stretch. Okay, that stretch, that closed band that you get is independent of the initial condition. In fact, what you can show is that in the quantum case, the band that you get, if you look at the center of that band, that matches exactly with the solution of the van der Pol oscillator. So then you have found that what quantum mechanics does is to add some quantum fluctuations. In the classical case, you had one trajectory, one line. In the quantum case, you have a band. Okay. Now the next thing is, of course, I don't have time to do, but this is something that perhaps you would like to do, is suppose I have many such open quantum harmonic oscillators, each one has got a different frequency. Can the system now synchronize? Then I will say that the system exhibits quantum synchronization. Quantum limit cycle 1, quantum limit cycle 2, limit cycle 3, limit cycle 4, each one has got a different frequency and I let them couple. Problem with quantum is that calculation becomes very tedious, simply because you have to basically deal with the Wigner function, and so therefore you have to deal with the density operator equation, the Lindblad equation. This is what is known as the Lindblad, which is a highly non-linear equation. If you have 2 oscillators or 56 oscillators, you look at the density operator of the whole system, okay, which you can take it to be the direct product of the density matrices of the individual oscillators, but then you have to do, there is no escape route. I mean, you have to do this calculation and see what you get, okay. And the way to see whether you have synchronization or not is to look at the power spectrum, okay. So if there is synchronization, you will get that the power spectrum has a single peak, okay. In fact, in the notes, what I have done is I have worked out a simpler situation in which you have a limit cycle oscillator of frequency 50 Hz, quantum limit cycle oscillator of frequency 50 Hz, that I have subjected to a periodic drive of frequency minus 20 Hz. And I want to see whether this oscillation frequency due to interaction with the drive becomes eventually like 20 Hz. Okay? And the way to see it is to look at the power spectrum, and of course these gamma 1, gamma 2 quantities will play a role, and so on and so forth. Okay? So I think this is about the time to stop. So thank you very much for your attention, and thank you. So please do the exercises, and not today, but let's say over the next 1 month or so. And if you have questions, then you can write back, okay, and I'll try to help you. But if you are interested in synchronization, then try to do those exercises, because the best way to learn things is to actually do it instead of having another guy tell you about it. Okay, because maybe he is bluffing, but you cannot bluff to yourself, I guess. So it's always good to do things on your own.
Excuse me.
Huh.